Hi, this is Maggie. In this video, we're going to use JUnit to write our own unit tests to test a method. Unit tests are used to test small units or pieces of a program. I'm going to use the definition of a unit provided by Naik and Tripathy in Chapter 3, Unit Testing, of Software Testing and Quality Assurance. I'll include a link in the description to the book. They write, syntactically, a program unit is a piece of code, such as a function or method of a class, that is invoked from outside the unit and that can invoke other program units. Moreover, a program unit is assumed to implement a well-defined function. In this video, we'll look at how to test a method. In the next video, we'll consider an entire class as a unit, and we'll look at how to design test cases for a class. So here I have a class called probability, intended to offer some basic probability functions such as factorial, combination, and permutation. So far, we have only implemented some methods to calculate factorials. Factorial is defined for non-negative integers. Factorial of 0 is 1, and factorial of integers larger than 0 is the number multiplied by the number minus 1 multiplied by the number minus 2, etc., down to 1. So, for example, 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. The first method, called recursive factorial, has a precondition that the value passed must be non-negative, and the post condition that it will return the factorial of the value passed according to the definition of factorial. The precondition is checked and an illegal argument exception is thrown if the value passed is negative. Otherwise, a recursive algorithm is used to calculate the factorial. The second method, called iterative factorial, is basically the same except it uses a loop rather than recursion to calculate the factorial. Now, there is at least one error in at least one of these methods. Let's see if we can write a thorough set of JUnit test cases to find the errors. A successful test case is one that uncovers errors, and I've guaranteed here that we'll be successful. Now, to write the test cases, let's first create a JUnit class for testing, and then we'll just think about the definition of factorial and the preconditions and postconditions of the methods. These methods and this functionality really do satisfy the condition of being well-defined, as this is a well-defined and easily understood mathematical operation. To create the JUnit test class, I'm going to right-click on the src folder and choose New, and then JUnit test case. And in the dialog box, I'm going to call this test factorial. I have the option of some different versions of JUnit, and I'm going to leave the JUnit Jupyter Test radio button selected. And I'm not going to check any of the checkboxes for special set up or tear down methods, as we won't need them here. If we decide we need one, we can always add it. So I'll click Finish. Now, much quicker than adding the JUnit build path to our project ourselves, we can opt for Eclipse to set that up for us. It asks now if we want to add JUnit 5 to the build path. So I'm going to click OK. And now over in the Package Explorer, we can see it's part of our project. OK, and here's my class, and we can see it has a method called test, and that has an @test tag before the method header. We can write as many test methods as we need. There's no guarantee to the order that the @test methods will run. It is a good practice to write separate testing methods for your different tests. That way, you know the exact environment under which each test is run. If you run several tests inside one test method, there's a chance, depending on the code, that earlier tests within the method will impact the outcome of later tests. This is more of an issue when we're testing a class which has state. Our factorial methods will basically reset each time we call them. However, we will follow the practice of separating our tests. It makes it quicker and easier to find the errors. So now let's think about what we want to test. We have our definition of factorial, and as it's a well-known operation, we can easily find the expected values for different inputs. For example, as mentioned before, 5 factorial is 120, and 0 factorial is 1. And we know that factorial is not defined for negative numbers. Let's begin with a simple test. We'll test that our methods will return 1 when we pass in 0. I'm going to change the name of the test method to test0 factorial returns 1. Now I'm going to test both of our methods. I'm going to write assertEquals, and then the value I expect, 1, and then the invocation of the method with 0 as a parameter, probability.recursive factorial 0, which we expect to return 1. So assertEquals is asserting that expected and actual results are the same, and then close parentheses. And then I'll do the same for iterative factorial. Now, two other things I can do to make the testing results easier to read. I can add an @displayName tag above the method to document the method in the test results, and I can add a string to the end of assertEquals, which is the failure message. So the displayName tag is followed by a parentheses with a string in parentheses, and I'll make the displayName check that both methods calculate 0 factorial correctly. Now we need to import displayName, and we'll let Eclipse add that import statement for us. And as the last parameter to each assertEquals, I'm going to add a string. Recursive factorial fails to calculate the factorial of 0 correctly, and iterative factorial fails to calculate the factorial of 0 correctly. So let's run our test case and see how it does. We just click the Run button. And the JUnit tab opens where the Package Explorer tab is. And this is very good. We have a red bar because our test failed. This is good because it means we wrote a useful test that found an error in one or both of our methods. Let's dig in, and then we can fix the error. So first, you see the displayName that we wrote for the failing test. If we had many tests, this would make the failure or failures very easy to find. It says check that both methods calculate 0 factorial correctly. So we know one or both of them are not doing that. And if I go into the failure trace in the pane below, I can see one of the methods threw an illegal argument exception. That's not right. We want them to throw an exception for a negative number. It looks like from the failure trace, it was the iterative method. So we go into probability.java and look, and sure enough, we're checking n less than or equal to 0 to throw the exception, rather than n less than 0. And input equal to 0 is fine. So let's fix that so it's n less than 0, and try again. And now we get the green bar. This is excellent. We wrote a test that uncovered an error, and we fixed the error. Now, what about those exceptions? How do we test for those? Let's write another test method. So @test, and then @displayName, check that both methods will throw an exception for negative input. And then void test negative throws exception. And now this syntax is a little different. We write assert throws, and then in parentheses we write the type of exception we are looking for. This will evaluate to true for the type of exception we put here and all of its subclasses. So we could put simply exception or runtime exception, but let's put illegal argument exception because that's more specific and that's what we're expecting. So we write illegal argument exception dot class. And then after that, we're going to put an executable. That is what's expected. Some code that when executed will throw an exception. So we do not put simply our method call as with assertEquals. We put a lambda expression. And this is quite simple because we are just invoking the method with a negative input. So we'll write open paren, close paren, and then an arrow. In other words, dash, close angle bracket. And then open curly brace, our invocation probability dot recursive factorial -1 semicolon, close curly brace. And now we can also put a string in that will be the message if this fails. So, comma, recursive method fails to throw an illegal argument exception on negative input. Now, this returns the actual exception object if it's thrown. So we can also assign that into a variable and then check the message if we want to. So for example, before the assert throws, illegal argument exception E equals. And then below that, we can assert equals, which will use dot equals to compare the two strings. The string we expect cannot calculate the factorial of a negative number, -1, and E dot get message. And then we can copy that entire block and reuse it for iterative factorial method, just replacing the message and the invocation. Let's run that. And we get the green bar, so we know that we're throwing exceptions for -1 at least. Are we done? No, we're not. Sometimes it's difficult to know what we should test. We've tested part of the definition of factorial, but we haven't tested the rest of the definition, whether we get an accurate factorial for non-negative, non-zero values. We should test edge cases. This is a definition that requires some kind of looping, either a loop or recursion, so we want to make sure that it works for edge cases and that there isn't an off by 1 error. Let's test for the correct factorial of 1 and 2 as edge cases. The values 0, 1, and 2 are quite special anyway. 0 is the additive identity. In other words, if we add 0 to a number, we get the number itself. And 1 is the multiplicative identity. If we multiply a number by 1, we get the number itself. And 2 added to itself is the same as 2 multiplied by itself. So it can also sometimes disguise an error. Let's write a low edge test case. So for example, at test, and then at display name, check that cases at the low edge of factorial calculate correctly for both methods. And then void test low edge factorial. Assert equals 1, comma, probability dot recursive factorial 1, comma, recursive factorial fails to calculate the factorial of 1. And then I'll write a similar test for 2 and redo both for iterative factorial. Now I'm copying and pasting, which is a great way to introduce errors. And if you read the chapter that I mentioned at the beginning of this video, the authors discuss mutation testing, a way to test the tests. What I'm going to do is read over my tests carefully to make sure the messages match the tests, and the tests match my intentions. Okay, and now that I'm sure they're correct, I'll run the tests again. And we get some more errors. Success! Let's see what we've uncovered. Obviously, it is our new test cases that failed, but I do want to point out that every time we're rerunning all of the tests. When we fix the bugs we uncover in one test, there's a chance we're introducing new bugs. So it is important that we run all of the tests every time in case we've accidentally introduced a new bug. Let's see what we've got. In the failure trace, we can see that the illegal argument exception was thrown for recursive factorial 1. How can that be? Let's look at the code. In the recursive version, we call recursive factorial from within recursive factorial, and we're calling recursive factorial with n minus 2, which is 1 minus 2, which is -1. That's not right. We should be returning n times recursive factorial n minus 1, which will call it with 0, our base case. That is an off by 1 error. Let's fix it and try again. And it fails again. A different failure. Now iterative factorial fails on a parameter of 2. Expected 2, but was 1. So somehow the 2 isn't getting multiplied in the iterative version. Let's see. We're counting down from n for int I equals n, I greater than 2, I minus minus. That's not what we want. We need it to calculate the 2, not end before the 2. We could write I greater than or equal to 2, or we could write I greater than 1. We could write I greater than 0, which would feel more complete and correct according to the definition, but would involve one more iteration in which we multiply by 1. Let's do that because it matches the definition. And we test again, and we get the green bar. Now, we could also do a test case for some middle range values, such as 5 and 10. We know 5 factorial is 120, because we can easily calculate that mentally, and because many definitions of factorial include a computation of 5 factorial. We can type 10 factorial into Google, and it tells us 3,628,800. Note that factorial grows very large, very fast. Let's write and run those tests. And those run successfully. Now, something we don't know is what the upper bound of this calculator should be. We are going to overflow our integer representation at 17 factorial. A long int representation overflows at 21 factorial. Even a double will overflow at 170. So it is important that we know the upper bound for which this method is expected to calculate correctly so we can test for that. That is another sort of edge case, and we don't know that, but if it's a large number, we will need to use a more sophisticated representation or method of calculation. So that is an introduction to writing your own JUnit test cases. To practice with this, I suggest you rewrite the test cases for the factorial methods, and then write some test cases for other well-defined methods. You can choose methods from whatever Java textbook you're using, or from other video examples on this channel. Once you can successfully write JUnit test cases for a method, you're ready to move on.